I'll share those recordings with you, and then you can look back at them if you want. So we did talk about arrays. We started and we went quite far. So we went until the first exercise, which is right here. Okay, so let's start out with this to start the day with a good exercise. So here's a budget constraint, very standard. So on the left-hand side is expenditure. C plus A is going to be assets, tomorrow's assets, discounted by some interest rate. And on the right-hand side is income or wealth, cash on hand. So Y would be income and A would be assets. And so we want to compute an array. So what does it say here? Use a comprehension to build a three-dimensional array. So three-dimensional array that we want to use to compute something like a consumption savings problem. Okay, and the three dimensions should be going down the rows should be current assets. Going over the columns should be current income, so Y. And going into the third dimension should be savings, such that then I can pick out a value that I'll call consumption at coordinate ijk of this three-dimensional array. It's going to tell me exactly how much do I consume if I'm at state AI, income yj, and I save so and so much. Okay, so I'll open the breakout rooms again. You just so what do you have to do? You have to open this website again, which is always here, Julia Bootcamp. I'll put that into your chat. Open that website, go to the thing for arrays, so number 3, and then you'll see on the just above here, so go back one, you see how comprehensions work. So you have to use this construct here in order to achieve what is asked here of you. Okay, so let's try this out. I'll put you in those rooms, and let's go. Let's meet there. Okay. Open all rooms. Chilling. Okay, so everybody's back. Good. Sorry, I've just been looking here. So how was that? Was that doable? Yeah. Okay. Great. Excellent. So let's just quickly look at one possible.
Rafa, did it work out the other way around?
Yeah, no, I didn't make it. I mean, when with Bahagan, we have a question because when I did the list, I didn't create an array for Y or A.
Yes.
I created everything within the comprehension, and then we were trying to do it, creating an array and accessing the array to construct this.
Okay. So
and
both things should work. So basically, here's what I did. Have a look. Is it too small again? Make it bigger. So here's the square bracket, right? Within that, you write your expression. The expression is this one. Goes so y plus a minus 1 over 1 plus r times a plus. So I've got three variables: y, a, and a plus. And then I just have to say how those things vary. So a has to be in 0 up to 2, so 0, 1, 2. Y has to be in 1 and 2. And a plus, so tomorrow's a has to be in 1, 0, 0, 1, 2 as well. Okay, and that's it. Okay, we'll use a as the iterator. So a here will be 0, 1, 2, and so on and so forth. You do that, you get this array, just this 3 by 2 by 3 array as we want it. Okay, so, and I think what Rafael said, you can, of course, also, you can create this outside. Okay, so you can create this before. If there's a, if you need to do that, so you can say the a vals could be 0 to 2. And then you would say a in a vals, for example. Same here. All right, you can do this. Those work both equally well.
So here, Florian, you're telling Julia that y can take values 1 or 2, and a can take values 0, 1, and 2.
0, 1, 2. Yes, exactly. So that's what we said here. A should be 1 and 2, and no, y should be 1 and 2, and a should be 0, 1, 2. So that's just how we specify.
And with one line, you can do that. Okay.
Yeah, I do that in one line. So the purpose of the exercise is to show you that in one line you can build extremely complicated expressions, right? You can see that when usually you have to write three loops for a, for y, for a plus, you just do it in one line. Okay, and it's I think it reads nice, and it's a nice way to build arrays. So that's why I wanted to show you that.
And with this, you get a 3-dimensional matrix.
Yeah, you see, so it returns a 3 by 2 by 3 array of type float. 3 means it has 3 dimensions, of course, and those are the 3 dimensions. I mean, that's the output. That's the first slice, second slice, third slice. Okay. So I use.
If you want to call it, I mean, if I want to see like what did you get in the third dimension, how do you?
Yeah, so we'll get to that. We'll get to how to access those things, how to index those things. That's the next topic. Okay, so let's just go there. It's very similar to MATLAB, but let's just see how that works. Okay, so those are called comprehensions, and they're really cool and powerful and very handy. We mentioned yesterday with Monse that you can also have interdependent indices, right? Like in this sum, you can have that the second j here is a function of I. Okay, then in which case you don't generate a rectangular shape, but just a vector. You have to get rid of the comma here. Okay, so there can't be any comma. It will yell at you because it cannot build a rectangular shape, but it will do that. So we'll just line them up one by one. Okay, so suppose actually we want to do that thing. So suppose I want to compute this this nice this nice thing. Okay, so one thing that I always like to point out with Julia is that you can get very close to the math, okay, with the language. So this is it. This is written in your paper. That's your model, and now you want something to compute it. Okay, so here's one way to compute it. You just build this with a comprehension. You build this, right? So here's I squared j to the 3. 4i in 1 to 3 as the first sum says, and j in I to 16 as the second sum says. And you build this S1, that will be this array that holds all the values, and then what it says to sum, well, then you sum over it. And that's going to be the result, 55,680. So that's nice, but it's not the nicest way. The nicest way is to not construct the array at all and use what is called a generator. So there's comprehension and there's generators. So look at this. There's round brackets and not square brackets. And there's a reduce function in the beginning, in this case, the sum. Okay, and so what this thing is going to do is going to accumulate the summation as you go along. It will never build the entire array. Okay, so we'll never allocate all of those numbers in a temporary array even, to then take the sum as I did on the previous slide. No, it will compute all of those numbers on the fly, go along and allocate very little memory and be super fast. Okay, so I mean this, if you compare this to the math above, that's just beautiful. Okay, so you say, well, you have sum, I squared, j3, 4, whatever the indices say, and that's it. And that gives you the sum, 55,680. Okay, so that's all nice and fun, but what about performance of this? So let's just put some numbers on this finally. Okay, so let's do a first benchmarking exercise, and we'll do that later on quite often. I'll use this package, which is called benchmark tools, which gives us timing tools. It's a bit more sophisticated than the base function at time. So at time is part of base Julia, which just takes the time of an expression. The benchmark tools is more sophisticated in that it recognizes that every timing you take in a computer is a random variable, because your computer is, if you take the time once, it gives you a result. You take it another time, it gives you another result. So because there's lots of stuff going on at the same time, there's variation. You have to kind of account for that. So this thing is just taking random samples, just doing it many times over. Okay, so what I want to do, I want to have two functions, f1 and f2. They have no input argument, as you can see. The first function is going to build the array, right? So that's the usual expression, the comprehension. You see the square bracket. The second function does the generator. So there's no square bracket here. All right, I just removed the square brackets. And then I call each function once to trigger compilation of those, because I don't want to measure the compilation time. I want to measure the runtime. And then I want to look at the output. So I call add benchmark on F1 and add benchmark on F2. And I store these things in B1 for benchmark 1 and B2 for benchmark 2. Okay, so let's quickly look at those. What's the benchmark of the first function? It looks like this, looked as a histogram. So what did it do? It took 751 samples. So it did that 751 times in order to see what's the timing. You see they're very different. Okay, there's a huge dispersion, which is interesting in itself. And so we want to look at the median, I guess. Okay, so the median time is 5.9 milliseconds to do it with the expression, with the comprehension, to build the temporary array. And you allocate 5.23 mimibytes. That's the binary version of megabytes. So just think of megabytes. So 5 megabytes allocated for this summation. Okay, that's quite a lot. If you do it with a generator, so no allocation of a temporary array, what do you get? 3.3442 microseconds, not milliseconds. So that's an order of magnitude less. And how many memory do you allocate? 0. There's no allocation of memory at all, because you don't build any temporary array. Okay, and so that shows you that this is very powerful. And if you don't have to allocate an array, just don't allocate an array and use those constructs rather. Okay, so then we can take with the benchmark tools function as a ratio function. So it tells you, you can take the median of the first and of the second benchmark and report the ratio That's very useful. So ratio says it's 17 times faster to not build the array. And in terms of if you want to, then there's a function judge, which does the same thing. So it will tell you what this represents. 1,600% regression if you do it in this way. Okay, so very bad. Okay, and so that's it. 5 megabyte instead of megabyte. Okay, so MIB is megabyte. It's the binary version of megabyte. Anyway, so you can see that makes a big difference. Okay, if you know those things, you can gain a lot or lose a lot. So that was the generator versus comprehension. Okay, so let's move forward and make progress. Ranges, we talked about those already, so we won't spend any time here. You know what that is right now. What is this? Just to illustrate a little bit. So here I can build a range. So I will bind the value of this variable here, which I call pin, to this slider. That's a slider here. I make it go from values 2 to 10, and now I can change the values by moving the slider around. And then I'll grab the value and put it in this plot. Okay, I'll say the range should have length points, whatever that pin is. Okay, so if I move this around, it will make more or less points. Okay, you can see the plot changes as I go, makes more and more points. And so that's, just to show this is a range object with different length. Okay, we'll talk about interactive plotting in one of the sessions if we get time. Otherwise, the notebook is there for you. It's very easy to understand. I mean, this, by the way, I'm a big fan of these gadgets, as Mark will tell you. I made him suffer a lot. That's basically how I work a lot with my models. And I really like those things too. I call those comparative statics version 2. So, you just have the model and you start moving around sliders and you see what changes. If you're as bad in algebra as me, that's the only option you have. So you just have to look at pictures. Okay.
Just one quick.
Sure.
Sorry, Florian.
Sure.
One question about this plot and the sliders.
Yeah.
If you would have, for example, let's say that slider pointing to a function. So this slider would be an argument of a function.
Yeah.
Julia will need to compute the function anyways, not for each of the values, but or you can compute.
No, it will compute. It will evaluate the function each time you change the slider.
Okay, but you could also assign it to the result of the function. Compute the function later before all the values.
Pre-compute it, yeah. You could pre-compute it for all the values that the slider exists, and then just pick the one with this thing.
Okay. Thanks.
So, yeah, but no. So you'll see. So again, there's going to be the last notebook. If you don't make it there, go there and have a look at it. The advantage of a fast language, of course, is that you don't have to do that. Okay, so it's not that you have to run your model overnight to compute all the possible slider values, and the next day you can look and move the slider around and say, oh, look how it changes. You want to do that live, okay? Because otherwise you have to wait 24 hours in order to use that thing. It's pointless. Okay, so that's kind of important that you can do that actually live. Okay, indexing. Right, we talked about that with Mark. How do I actually get the values out of this stuff? So, wow. So we have 2 ways to index, which is kind of nice to know. So that one thing is called linear indexing, by which we mean if this is an array, it's a matrix 2-dimensional array, we build it with this expression. You can see the storage order in this matrix. You see it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This storage order of an array is called column major. So it goes, so the first direction is the column. It goes down columns like this. And so it tells you how the array is laid out in memory of the computer. So that's how it's represented in the computer. This is different from row major. Some languages go row first. I believe MATLAB does that, and certainly Fortran does that. So you have to know that, okay? And it has performance implications, so it's much faster to traverse arrays in storage order. So go down column first, okay? Now, for us, this does matter because the linear indexing is just going to choose the ith element of the array, even if the array is high dimensional, there's a unique number of each element, and that number is called the linear index. Okay, so you can read it off here. Element number 8 is this one. Is this guy. Okay, that's element number 8. And if you say, give me element number 8, it's going to give you that one. So if you just if you just take x and give me the 8th element with one index, you can see this is a 2-dimensional array, but I can give you one index only, in which case it's going to look for the linear index in that array. If I give it one index for each dimension of that thing, in this case 2, it's going to look for what is called the Cartesian index, something, I guess, which is more immediate for you and also for me. So, you know, if you have 2-dimensional array, you look for element 1, 1, which is first row, first column, 1, 3, first row, third column. So that's the number 7 here, and so on. Okay, so that you can do, but you should just know that this exists. In particular, for very high dimensional arrays, linear indexing usually is faster. I mean, we're talking about 10-dimensional arrays or something, because of course, if you do a 10-dimensional array and you have to look for all of these 10 numbers, there's some small computation involved. Okay? If you know the exact linear index, you can do that right away. Right? But that's a small consideration. Colon means all. So 1, colon means the entire first row. That means the entire first column. Okay, so that's very standard. Same everywhere, I guess. Again, the 4th linear index in storage order. And there's a reserved word, end, which gives you the last element in the array. Okay, so I think that's very similar to what you know from MATLAB. You can also do logical indexing. So you can create a vector. Here I call it which ones, which is going to be false or true, indicating which element of the data array X you want to pick. And then you give this logical to the X, you stick it here. It's going to pick the ones where you have true. Okay, so that's basic. Okay, quick question. That's one for Mark. So he's going to be able to tell us that now. So tell us the consumption C associated with all savings choices, AT plus 1, if A is 1 and Y is 1, by indexing your cons array from above. That is, just index cons in the corresponding indices and use this for the savings dimension. So we want to have for all savings choices, how much do we consume if A is 1 and Y is 1? Okay, so that's a simple indexing exercise. So if we have cons here, so that's cons, that guy. So it asks us to look at if A is 1 and Y is 1. So we have to go back and figure out which indices those were. So A1, that's the second index of A vals. So A vals second is, there's no A vals here. So A vals second is 1. And Y here is 1 and 2, so it has to be the first index of Y. So we can just do the following. We just say, okay, cons. Now we want to index this with the square bracket operator. I want to say at index 2, this is A equal to 1. Y has to be the first index because it's equal to 1. And now I want to know what are all the savings choices. So I'm going to put a column there to give me all the savings choices. Okay, and that's going to return the consumption values associated at this state of the state space, let's say. Okay, so if you save nothing, you will consume 2. If you save 1, you will consume this. And if you save 2, you will consume this. Okay, so that's just how to answer a question like that and how to index. Okay, you've seen it's, I think it's identical to MATLAB, to be honest. So there's not much news here. Okay, good. Let's move on. Here's a bit of news. So now we know how to get values out of this, but how can we put values into this or change values? Okay, so how can we modify the value of an array? Well, so first thing is going to be simple. So let's just grab an index, x1 and 2, and let's just assign a new value to it. So here I want to assign -9, and I'll look again at x, and now here there's -9 at the corresponding 1, 2 index. Okay, so that works fine. We're happy with that. what happens if we do this? So here's a new vector v. It's a vector of 10 ones, looks like this. And I want to do this. I want to say the index is 2, 3, so the second and the third number should now be 2. And I hit enter and it says this. Oh my God, what does it say? Argument error. Indexed assignment with a single value to possibly many locations is not supported. So it doesn't want to do that. Okay. Perhaps use broadcasting instead. Okay, so what's going on? So the assignment so here, this thing here says assign. The assignment wants that on the left-hand side of the assignment and on the right-hand side of the assignment, you have the same shape. Okay, even though for you, it's totally obvious what this should do, and to me as well. Julia is very strict here. Okay, what you're doing here is not correct in the sense that on the left, what do we have?
2 elements.
Good.
One in the left 2 and the right 1, right?
Yeah, in the left here, what do we have? So what is this object?
It's a range.
It's an array, the other one is scalar, no?
Exactly, it's an array. Okay, it's not a range. So let's just quickly check that. So you just do type of v 2 to 3. That's a vector. Okay, and on the right hand side, of course, that's an int. Okay, so the left hand side and the right side are not the same. So he complains that that's not going to work. He's not going to do this assignment. But he gives a good error message. I mean, really good for Julia. It says, perhaps you want to use broadcasting instead. Okay, so what is broadcasting? That's what we have to figure out. So the left and the right is not the same. What we want is to do this assignment element by element. Okay, that's what we had in mind because we were MATLAB users and that's how stuff works for us. But really, that's what the operation is supposed to do. It's supposed to assign to each element of this array that value. Okay, so we have to be explicit here and use the dot equal. You can see that the dot marks broadcasting. So it means we broadcast over an array a scalar operation. Okay, so assign to each index of this array the singular value 2. And if you do that, you see that it works. You have 2 2s now here, and the other ones are as before. Okay, so that's something to keep in mind, and we need that. So it's so ubiquitous in Julia that we really need to think a little bit about it. It's you don't have so for example in R or in MATLAB you can just use functions that are built in on scalars and arrays in the same way. Okay, we'll just do this work for you. Okay, so for example here you do exponential of a vector 1 and 2. That doesn't work. So Julia says quite explicitly there is no method matching exp of a vector. Just there's no such function. Okay? Whereas in R there is such a function, and in MATLAB as well. There's such a function because the developers of MATLAB went and wrote a function that does exp on each element of the array, just you don't see it, okay? And it's hidden away from you. So what do we have to do? Well, we can actually compute exponential over a vector, thank God. We just have to use the dot here, see? And which means broadcast exponential over this array. Okay, and you see that then it works. Okay, so that's good. Now, a little bit of preaching, this may look a little bit awkward. Okay, you think, okay, my God, well, why do I have to add the dot now? More work for me. And if R and MATLAB can do it so well, why should I have to worry about this? So that's a valid point. But the good thing about this is that this dot stuff is going to work on every function, in particular on your own functions. Okay, so if you write a function that does something on a scalar input, you don't have to worry then about writing a second function that's going to take an array input and apply the stuff to all the elements of the array. You will just be able to use a dot in front of your function name. No more work from you required. And this will generate a very efficient version of your function that works for this array. Okay, so I put a couple of links here. There's a nice blog post here and another blog post there. that is only for the very not the faint of heart. Okay, so you have to be a bit interested in this stuff to have some fun out of it, but then it's a lot of fun. So the way this works is really quite amazing, even if it's, in particular, if it's multidimensional. So what the language will do, it will unroll your loop and compile a unique instruction for your CPU. So it's kind of amazing what's going on. But we won't dwell on this. We will just say that all of this stuff, the dot, broadcast, and those things, they will work even on something like CUDA. CUDA is the language that runs on GPUs. You know, the graphical processing unit, the things that go so fast, and in which you can do very fast array operations. You write your Julia code in exactly the same way. You do nothing else. Okay, you just do this. You have a dot in front of your function, after your function, in front of your array. If that array happens to be allocated on your GPU that runs CUDA, it will just work. Okay, you don't have to know anything about the CUDA language itself, or I don't know what, or how indexing works on the GPU, because suddenly that's zero-based because it's a C language, I don't know what. Okay, so that's the powerful part. So the broadcasting operator is very important. Okay, question. What is this going to do? So V was this array of ones, 4 to 7, and now on the right hand side I have 4 zeros. What do you think this is going to do? Is this going to work?
Yes.
Yes, it's going to work exactly as it does here, because the shape is the same. There's 4 numbers on the right, there's 4 numbers on the left, so that's okay. Okay, that will work. And indeed it did. Okay, so let's look at V now. So we set those 4 guys to 0. Okay, it worked because they had the same type. Okay, brilliant. Let's give a name to that, and we call that a slice. Okay, that part of a vector of an array, we call that a slice. So let's call it S. So S is equal to those 4 indices of V. Now the real question is, what's going to happen if we modify the values in S? What do you think?
How does it store S?
How does it store S?
Mm-hmm.
What do you mean?
So, well, in some languages, S would be a separate vector.
Yes.
Here, does it refer to V, or it's a part of V per se?
Yes, exactly. I guess that's the real question. So how does it? So that's what I wanted to ask from you. Just give me a guess. What do you think is going to happen? So if I change S now, what's going to happen to V?
Nothing.
Nothing. Well, let's try. Okay, so here's S, and that's those 4 zeros. And now let's set one of those values. So let me grab the second one of S, and I set it to 333, such that S looks like this: 0, 333, 0, 0. Okay, let's look back at V. All right, go back to V. V, nothing. Okay, so V did not change. Okay, now you can either be surprised or not. It depends how you think about those things or what your background is. But basically, the question was of Vahang, how does it store S? It's exactly the right question. So it turns out that this operator makes a copy of the data. So if you take, a slice with the square bracket operator, you copy the data to a new array. Okay, it's allocated on a different set of memory, and hence this is not affected. So V is untouched. We have a 333 here somewhere. There's an alternative. An alternative is called views. So if you don't want to do that, sometimes you want to do that, but sometimes you don't. Suppose you have a very big array and you want to do something on a portion of that array without copying data around, then the view is the right thing for you. Okay? The view will look into the array, as it says, create a window, and operate on that. So here's how a view is created. There's a function view on the array V at those indices, and we give it a name again, W. W is let's call it the window. What's the type of this? It's called a subarray. Okay, it's a subarray of the data, same data type, and it tells you how the indexing works. So it indexes into the parent array. So B is going to be the parent array that holds the data. And we modify that. So let's modify the element 3, 4 of W to -999. Then you'll see that V, the parent array, did change as a result. Okay, so we have the 999s here. And so those are the two ways in which you can operate on arrays. One thing is going to make a copy, which sometimes you may want to do that. The other thing does not, which is not sometimes what you want to do. So I think that's really important. For example, if you're into, we mentioned value function iteration. Suppose you have a big model where you have to integrate over the value function. So there's some shocks in the model. And you store the value function such that those shocks vary over different dimensions of some array. Suppose there are 3 different shocks. So you have to integrate in 3 different directions over that array that represents the value function. Now, one way to do this is the traditional way. You just copy those slices out on the side, you integrate over them, and then you put them back into the result, the expected value function or whatever. With a view, that's much simpler because you don't have to copy back and forth anything. You just take the view on the value function, you integrate over that, and that's it. You just leave it there. Okay, no copying, nothing. Well, that would be a good use case, maybe.
One question: is this also? Oh, sorry, Monse, go ahead.
All right, go ahead.
Is this also just a function, or it's going to create an array? So is it going to create a data structure in the memory or not?
No, it's not going to allocate any new memory. It's literally a way to view the array. It's just it's like if you think about the big array, this view function is going to take it's just about indexing. Okay, you see, it has to know what is indexing. So that's the parent array. So that's going to be V in our case, and it has to know what you mean when you say W3. So what are you referring to? Okay, and so that is just stored somewhere. It has this indexing rule. It knows if you say W3, what you really mean is V at some address. Okay, so that's how it works. It's just it's like a mask on your original array V that you use in order to work on the indices.
So my question is not related to that so much, but it came to my mind now. So in MATLAB, you always start with some clear so that the variables that were recorded, they delete and so that you don't mess up.
Yeah.
What do you use here for that? Because, yeah.
You start, so I didn't understand that. So you have some.
So to delete the values of the variables you had.
Yeah. To derive the values of the variables. Sorry.
Yeah, you want to start from 0, okay?
To clear the workspace, for example. If you want to clear the workspace and start without any new arrays.
Right. Yeah. So there's no such thing as clearing the workspace. Okay, so that doesn't work because that just doesn't work. Okay, you can set values to 0, but you have to do that manually. Okay, so you grab V and say now V is equal to 0, and then V is a scalar that's 0. But you cannot erase all the variables in a thing. You would just have to start a new session. Okay, but so keep in mind that that's not the way you're supposed to work with this language. Okay, the way you're supposed to work is to write functions. And inside a function, you have total control about what a value is. You just, it comes in and you say, the start of the function, you're 0, for example, or whatever it has to be. But that's the main difference. It's not a scripting language as it is. So you don't have to run a script where on top you erase everything and then start from scratch. That's not how it runs. Okay, so if you want to do that, you have to run a new fresh Julia session. Start it again, and then you're sure that there's no dead values hanging around, and then you can do that. Okay, if you want to know what values are currently in a thing, you can call the function bar_info. Okay, bar_info is going to tell you what is all there. So now this looks for me, that looks very bad because in Pluto that doesn't look great. But here you would have the variables in the global scope. Okay, so for me that looks really bad because in Pluto it doesn't make any sense.
Thanks.
Okay, so view, there's also a macro for view. So add view is going to do the same. It depends what you prefer. So you do add view of V at some index location, it's going to take the same thing. So it's going to take this thing and wrap it into where is it? Into this expression. Okay, it's going to write this for you. Okay, so if you think that was too hard to write, this is going to do the job for you. All right, matrices.
What's the difference, Florian, between adding the at or not? I didn't understand.
So functionally, there's no real difference. Okay, this is just to make this. If you think this is nicer, you can use this expression. It's going to do exactly the same as the view function itself. You can just write it in front of the thing. It's going to do like this. There's just two equivalent ways to do this. And we mentioned already macros. They change your code. So in this case, it will grab what you wrote here and put it inside the view function. So it's a very simple macro, but it does that for you. There's very much more elaborate macros. Like for example, the benchmark macro is used above. But those are things that modify your code. Okay, matrices. Right, what do we have here? Here we build another matrix with a comprehension. So M, 1, 2, 3, 4, 11, 12, 13, 14, and so on, just some numbers. Indexing works exactly the same. So you can index ranges into both dimensions as you're used to. You can reshape this with the reshape function. Okay, you know that. It works exactly the same. Again, notice the column major storage. So it goes first into columns and then into rows. Okay, sometimes you want to get rid of all the dimensionality information of an array. So if M is a matrix, it has 2 dimensions, you can just get rid of that, throw that away, and just get the data values. Just get a 1-dimensional array, which you do with this expression. So which means basically all values in storage order. And it's the same as calling the vec function, just vectorize an array. Okay, so if M is a 3-dimensional array, you call vec, you get a 1-dimensional array. That gives you back the values in storage order. Okay, so that was that. Quick introduction to, sure.
Since MATLAB and Julia have different, you say that one is column major, the other is row major. That means that the reshape of the same matrix would give different results.
Yes, absolutely.
Okay.
Absolutely. I mean, I'm not even sure that that's true, but if that's true, the column and row major business, then yes, you will have to be careful with that.
Okay.
So, you know, in practice, you would have to transpose the matrix somehow, right? Or permute the dimensions somehow. But yeah, those are things you need to be careful about. Okay, good. So let's see what else we could do. What do we have here? We did, okay, defining types. Maybe we're going to make it through all of them. So let's see. Let's just do this. 4, defining types. I think now we're going towards the highlights. So it's gonna get pretty cool now. So data types, yes, we talked about those, of course, many times over. Right, nothing to say here. I load some packages in the beginning. Let's see. So I think we mentioned that Julia has a very rich type system already. So like built in, there's a bunch of types, but that's not very. I mean, you know, many languages have that. So all languages know how to represent a complex number or a float or an int. So it's all good. The manual is very good here again in this. So I would recommend you going there and reading about this. What is the real power of Julia? Or one of the real powers of Julia is the ease with which you can create your own data types and how you can work with those. And so that's, I think, going to be part of this lecture. Okay, so we talked about multiple dispatch. We said different types will trigger different behavior. And let's look at the type tree. And there's a couple of functions that we can use. For example, subtypes is going to give you what are the subtypes of a certain data type. Okay, so for example, if I call subtypes on float 64, it gives me back an empty array. There are no subtypes of float 64 because float 64 is kind of the lowest. It's kind of a leaf of the tree. If you think of a tree, the last thing you get to is a leaf. You can't go any further. Okay. Right, but what is before, what is above float 64? It's called super type of float 64. That's an abstract float. Okay? Abstract float is some sort of float supertype. Okay, but what is above an abstract float? Supertype of abstract float is a real. Okay, so all right, real number. And what is above a real number? We call supertypes. Now I call it an S. On real, I get real, number, and any. Okay, so first real, then there's a number, and then there's any. Okay, so that's good. Let me just quickly show you this. If I print the type tree of the number type, which is this one, I get this picture. So below a number, there's complex and real. Below a real, you can have abstract floats. So there's these different types. Those, right? So there's some different floats. You can have abstract irrational. As irrational types, you can have integers. Those are reals, Boolean, signed, unsigned. You can have rational numbers, p-value, test stat, etc. Okay, just to illustrate how, for example, the part of the type tree for numbers looks like. Okay, now we've seen that any is on top of the type tree. So any is kind of the highest super type. It's the most general thing there is. And so you need to know that that's the least specific data type, and everything can be any. And so I asked you for a picture, but I couldn't make the picture. I just showed you the picture. Okay, so on top of that, there's any. Right, so the base, Julia-based system, I'm not sure we have to lose much time here. There's any on top, and then there's all of those things at the bottom, so that's fine. Abstract and concrete types. Okay, we've seen abstract float. So what does that mean? That doesn't do anything, the abstract type. It's just a way to organize the other types below a little bit. Okay, so we've seen that below abstract float, there were float 64, float 32, and so on and so forth. So these abstract types are just a way to group those data types into bins. Okay, then there's going to be concrete types, for example, float 64, with which we can do actual work. Okay, so we can use those. And then there's going to be custom types. And that's where we're going to start, being a bit more interested, because those are the ones that we can create. All right, so we can define our own. We call those data types struct, very similar to MATLAB, I believe, or C. You have structs there. So it's just something that groups stuff together, right? There's a key distinction between mutable and immutable structs. So if you write struct like this, by default, it's immutable. Okay, so we'll see later what that means. But basically, here you have struct A. The struct is going to have a name A, and it has two elements in it, X and Y. Okay, those are the field names of the struct. And next to it, there's a mutable struct B, which we can mutate, can change. Okay, same names X and Y inside. Okay, once we've done that, once we've defined the struct, we can instantiate it or we can construct it. So we can build one of those. Okay, this is kind of the template, and this is how you build one of those. You just use the name of the struct, and you give two arguments, two numbers for each field. And it's going to fill in. Yeah.
Just maybe I lost it, but what is the difference then between a struct and a dictionary that we saw yesterday?
No, it's a good question. So you will see that later. You cannot, the main difference is that you cannot specialize functions on dicts. Okay, so dicts are really a data container. Whereas these types here, you can give, you'll see that, okay? You'll see that what we'll do later on, you can never achieve with a dict.
Okay.
Because a dict is too general, basically. You can't hold anything, as we said. And so that's going to be the main difference. Okay, so what do we have here? A, right? A has 1, 2, x1, y2. That's the content of A. And B, I create a B. B has 3 and 4 in it. All right. So we can access those with the dot operator again. So b dot x gives you back 3, and b dot y gives you back whatever y is 4. Okay, so far so good.
The variables x and y were already defined before, right? That's why.
Exactly right. But so you can see that that doesn't matter, okay? Because those x and y's, they're specific to A. They live only inside A. Okay, you know that Pluto complains if I define x. I redefine x. It doesn't even allow me to do that. It says multiple definitions for x. But that's specific to Pluto. So if that were a normal Julia REPL, like like this one. So I can do x is 3, and I can do then x is 4, and now x is 4. Okay, so that's basic. Inside Pluto, I can't do that because Pluto is very picky. It wants unique values that it then updates all the time. That's on the side. But yes, here that's inside some. That's a local scope again. Okay, so x only exists inside B. That's why when I want to use it, I have to do B dot x and not x only. Okay, so it's inside.
Okay. My question is this 3 that appears there. B dot 3 is equal to 3. This 3.
This one.
The result is 3, right?
Yes.
So this 3 was defined before. Where does this 3 come from?
Yeah, it comes from here. You see, I created it like this. I set it up like this.
Oh, okay.
You see?
Okay.
Okay.
Yeah.
Exactly. Good question. So I set it up like this. If I type B3, 4, it automatically sticks 3 into X and 4 into Y. Okay. And so what you see here, what I'm doing here, this is a function. So once I create the struct, Julia automatically creates a function, which is called the constructor. Okay. So that function is, and there's a default constructor. This is the default constructor, which just builds the array with the values you give it. Okay. And okay. And so let me just quickly say that, of course, you can be much more sophisticated with this. So you can create an actual function that will have the same name as B. You can create it even inside, in which case it's called an inner constructor, and which you can then, suppose you want to build a very complicated data structure. Suppose you want to build a model. Okay, so for example, mutable struct instead of B, you would write mutable struct model, and that model would have to hold a bunch of different things, some arrays, I don't know what, some stuff, some parameters, and then you want a way to build that model quickly. Maybe like we said before, Luis, you want to build that model for a certain set of parameters, right? So then you would have a constructor that takes some keyword arguments, your parameter values. You give them those parameter values, like suppose there's some alpha in that model or whatever. You say alpha equal to 1/3, and it's going to build the struct with all its contents in a certain kind of way that uses your input alpha equal 1/3. Okay, so we won't talk much more about this, but you can easily look that up on the manual, how to have more fancy constructors than that. Okay, it's a bit too far off for now. But don't worry about it. We'll see an example later, actually, now that I think of it. Okay, now, why on earth am I dragging you through this? Like, what the hell does he want with these types? So why do we want to define new types? Okay, I'll give you an example. There's an example where in many math operations, we have pairs of numbers with 2 numbers. And there's just a couple of examples. For example, 2 numbers could represent the rectangle that has a width and a height, or it could represent the complex number with a real and an imaginary part, or it could be a vector in 2D that has 2 components. Okay, you could each of those represent like that, x, y, whatever, a tuple. Okay, in this case, you could say a rectangle for me is this 3, 4. That means a rectangle for me, and it means width and height. Or you could say a complex number. I'll call that C. That could be 3 real parts, 4 imaginary parts. Or you could say, oh, 3 and 4 is a position vector in X, Y space, and I'll just call that 3, 4. Okay. So all of those things work in the sense that, then you write a function that does something to a rectangle, but they're not very clean because, of course, the representation is the same. And the only way that you will know which is which is because you called it rectangle or C or whatever, and you wrote a comment next to it. Okay, so I think you can see that that's not very safe. Okay, because I mean the tuple is a tuple, it's just 2 numbers. Okay, so we can really see that there's something wrong here. So what we want to have different behaviors for different data types, even if they store the numbers 3 and 4. Okay, let's look at this. So let's define a new type, and then we make a break. So the new type we'll define has a name. It's called rectangle. It has 2 fields, width and height, and I will say that they have to be floats. Okay, I can do that with the 2 columns. I can say these have to be floats. Again, struct is a structure. type annotations, and then we can create it as we did before with the default constructor. Just say rectangle1 2.5 creates for me a rectangle data type with width 1 and height 2.5. Okay, we were that far already, but now let's make a little break, 5 minutes, and then we'll see how we can work with this data type. Okay, see you in 5 minutes.
Bye, Florian.
Hey, Rafa.
Hey, Luis. Are you going to take a break or?
I don't think so. No.
Yeah, because I want to ask you something about the previous exercise about the budget constraints. I don't know if I can share. Well, I will put it in the chat because I have created it in 2 ways. First way was exactly like Florian did. Okay, like iterating on the loop like that.
Mhm.
You know.
Yes.
Like not creating the array for y and 80. But then with Vahagan, I was thinking that you may want the grids, right? If you are, I don't know,
Yes.
solving things. And then I was doing it in this way. And it works. So basically I get a consumption too. But then I cannot get my head around how to compare the first one with the second one. Because I get in very different orders and I'm not really understanding.
In different orders.
Yeah, because I think that's what you asked about the shape of the matrices, because the first one is basically a 3 by 2 by 3, and const 2 is just a vector of length 1. I mean, of
No,
column.
you need to put the. Isn't it the comma that is missing?
With the comma, it doesn't work because
I got this. It doesn't work. Why?
Yeah, I don't know why, but
I know
okay.
I know why, because I did this mistake. If you put comma, you don't put 4 again. So it would be like for A in a grid, comma, Y in Y grid, then it would work.
Oh yeah. Oh, okay.
Yes, exactly. So if you want to build the array in a certain shape, you have to put the commas.
Yeah, because
I made this mistake.
I pasted in the chat.
If you put the comma, you don't repeat the 4.
Yeah, I see. Because I pasted in the chat because I solved it first, like you did, without creating the Y and the assets. Yeah. But then I thought you may want to keep the grids for whatever reason.
Yeah.
And then I did the const 2 thing. But then I couldn't figure out how to compare the 2 arrays.
Yeah, exactly. So look, it's about this thing. It's about this example here. So if you get rid of the comma, here's a comma missing.
Yeah.
Then you build a one-dimensional array that just iterates over all of those values.
Yeah.
However, you don't want that. In this case, you want it to have where's my thing? You want it to have this, right? So you have your array outside. So I think I did what you wanted here. So avals is an array outside. Mm-hmm. You just stick it there.
No, yeah. I did it. I did it like that as well. But what I meant is that, for example, in the chat, the const 2 will be just a vector of length 1, and the const at the beginning will be just this array with this particular form. What I wanted then is to compare the 2 things, right? To see how each element corresponds to each position. Yes. And that was like, I was trying to wrap my head around that. And
no, but that's a good exercise. So that would totally work, right? So const 2 has to have the same values in it as const.
Yeah, sure.
Just you have to figure out what's the ordering.
Yeah. That's what I was trying to.
So basically what you want, const 2, if you has the linear index of the values in const. So if you do, so let me just do that. So how did you do that? Const 2 is just this, and you get rid of that stuff. That's const 2.
Do you need the 4 after the avals?
Probably, I don't know.
Because this is what also I was confused. about.
Okay. Right. This is an 18 element vector.
Yeah.
And so this is, so cons is this array. So let's do one thing. Let's look at this. Let's do one thing. So let's put those next to each other. So hcat of cons2, which is this vector.
Yeah.
Cons, but as a vector.
Yeah.
Let's see what they look like.
I did that and then I wasn't
Okay.
because what I think it's doing is putting the first dimension of cons all stack, then the second dimension, and then the third one. But I couldn't see all the numbers because you have the 3 dots in the middle, so I wasn't sure how to do that exactly.
Yeah, so that's what it's doing. Yeah, so those are tricky questions, how to index those things correctly and not get messed up. But good.
Because in MATLAB, there is this linear index to matrix index function. And yeah, I would know how to get that in MATLAB, but
yeah, so
here wasn't.
It used to be here as well. Not sure where it went. There was this int2, but that's gone. So let me just quickly think about this. So
well, I mean, it doesn't matter. So
in MATLAB is into set, no?
Yeah.
Yeah, it was exactly the same here, but then yeah, you have to look a bit at yeah, index linear, all of those things. So it will be in there. There's a way to convert those for sure.
Okay. Okay.
Yeah. Okay. So let's not waste too much time here. Good. So we were stuck here. Now we have a rectangle. And so now let's see what we can do with this. First thing, we can see whether that's actually a rectangle. So let's call type of R. It says it's a rectangle. Okay, great. R is a rectangle. Yes, that's true. All right, awesome. Now, obviously, we can get the information out of it by using our dots. So R dot width is 1. R dot height is 2.5, exactly as we specified it. So that's good. Okay, let's create a new rectangle with different height and width. All right, R2 is going to be 3 and 4. Okay, so of course that doesn't affect anything in R. So R is untouched by this thing. So it's got nothing to do with a different object. Okay, so R width is still 1. Okay, so this got nothing to do with each other. So we use the template to build a new object. We call those things composite types, okay, because we can group together different things. So now we have 2 floats, but they could be anything. And now we can, well, so mutable versus immutable, we said, so this rectangle was immutable. So now we want to change it. It's going to say, no, you cannot do that. It's immutable. You cannot change it. Okay. So we want to have an immutable thing. For example, you would just write immutable struct in front of it. So what you want to use depends. Okay. So here I wrote, it usually leads to faster code. I mean, that may be true, but you have to be very specific about, your use case. Of course, if you want to change the contents many times, then you need an immutable struct because those are built for this purpose. If you have something that's going to stay the same all the time and then you throw it away, then you can have an immutable thing. That's fine. But I mean, that's not very important. Yeah. Most of the times you use a mutable thing if you have a model or something, because of course you want to change the content all the time. Okay, so here's a nice question. I want you to create a mutable struct, which is going to be called endpoint, like my point. Okay, endpoint is going to have 2 fields, x and y. They have to be restricted to be of type number. Then I want you to create an instance of that, little m, with those values in 1.5 and 4.1. And once you've done that, you'll change the value of y to 3.1. As you have to do this operation here. Okay, so let's see if we can do that. Break rooms, recreate. Let's go.
Hi, Florian. So just we were testing these structs, and even if it is mutable, you cannot change the type of the things that you define, nor you cannot add things once the struct is defined, right?
That's exactly right. Yeah, once it's created, you're stuck.
I see.
Yeah, you have to start a new session. So that's
Okay.
really
Florian, how do I clear a variable in a given session?
Yeah, so I mentioned that before. You can clear for example, if you allocate X and you say you can't clear it, you can set it to 0. There's no way you can delete anything. Okay. Which with a variable is okay. As I said, you can set it to 0 or to whatever. But with a new struct, that's really annoying because you cannot erase it. It's there. Why is this the case? Well, it's there because you tell the language there's this new data type. It's called endpoint. It looks like this and that. It has 2 components, blah, blah, blah. Save it. Okay? And so it compiles it and it exists. At that point, you can't change it again. Okay, so that's very annoying. That's one of the reasons why we often work when we do these things. So you don't do that in your terminal. You do that in what is called a module. A module is all the packages are modules, by the way. So these are just little, regions that define a unique namespace. So they just group stuff together. And so within the module, we create this new type, try it out, and each time we reload the module, throwing away everything that is in global space, replacing that basically. Okay, so you're not stuck with this stupid behavior. Just to tell you that, don't have to worry about this. But indeed, in your terminal, if you have once you create your endpoint, it's there. You can't change it anymore, which is very annoying. Okay, good. So I hope that you managed to do that anyway. So here's my endpoint. Let me just do this. So endpoint, well, very simple. It could look something like this. Mutable struct endpoint X number, Y number. We said. I just grab this guy, create it here, and then we said to create one instance, M would have been endpoint with what 1.5 and 4.1. So just give this here 1.5, 4.1. All right, M is here, and then we wanted to set MY to a different value, 3.1. Okay, so that worked awesome because we set it to mutable, so we could actually do that. Okay. Very good. You wanted to call type of M. It will tell you it's an endpoint. It's my point. It's the point I created. Okay. Okay. So far, so simple. Let's keep going with our little rectangle. So that's fine. We have this new data type. Now, what can we do with it? We can define functions for it. So here I create a new function called width. The width of a R, which is data type rectangle, should do what? It's a one-line function. It should just return the width field. Okay, so very simple. I call width on R, it gives me back 1 because that's stored in the width field. If you call width on something else, for example, the number 3, it throws an error because it says there is no function, there's no method matching width for an int. Of course, there's not because no one wrote it. Okay. All right, so it's very common in Julia to have generic functions, so stuff that works with any input you give it, just to make sure. So think we define a function area on a rectangle, which would be, as you well know, width times height. And we will have a second version of this, which will just return the input, just to make sure. Okay, so then if I call area on R, that gives 2.5 because, well, that's how we set the values. However, if I call area on 17, which is a standard int, it's got nothing to do with the rectangle, it still does something, it gives you back the input. Okay, so you will call this a generic function, and this is a generic method and a specialized method. Okay, so we didn't do anything. So if you give it hello, it's going to return hello, and that's fine. Okay, but it doesn't make much sense because, of course, well, there's no notion that if you give a string to area, it gives back the string. So it just doesn't make a lot of sense. Okay, now suppose we create a circle type. We don't only have a rectangle, but also a circle now, and want to have a new method, area for circle. And so that's fine. Julia will just choose the right version of area, the one for circle, in order to compute the area of the circle. Okay, so that's the idea. You know, you have this thing area, you apply to different concepts. If you put it to a rectangle, you have to do it one way. Circle, you have to do it in another way, and so on and so forth. And you can just keep defining those methods, and that will then execute the right thing. And again, this idea, I said it so many times, is called multiple dispatch. So the fact that you will choose the right function to execute based on all the arguments that were input into the function. Okay, so it seems like something very simple, but that's a very deep thing. So you know, so you just have one function name, and depending on what type of data you give it, it's going to do different stuff. Okay, for example, look at the following 3 calls to the plus function, and they each call different methods defined in different locations. And you can even click on the link to see where the methods are defined. We did that before, so let's quickly do that. So here is a complex number, 3 plus 4 imaginary, and we do plus. Okay, we do CC plus CC. That yields 6 real parts and 8 imaginary parts. Okay, so there's a function inside Julia that knows how to sum 2 imaginary numbers. If I just type plus, it says there's a generic function with 296 methods. So there's 296 ways with which you can use plus in Julia. For example, let's look which version of this is called if we do this thing, we sum 2 complex. So it says it's that particular method, it's the plus for Z and W, which are complex, and it's defined in this location. Okay, so if you want, you can quickly look at this. We go there, it's going to put us to the GitHub of Julia, it's going to put us to the line where this method is defined. Okay, so how do you define it? You say plus, that's the function name. First input is Z, a complex, W complex, and then how do you create a new complex? Well, you call the constructor of complex. How do you sum 2 complex? Well, you take the real parts, add them together, and you take the imaginary parts and put them together, and that thing returns a new complex. Okay, so that's how these methods are defined. You know, there's a different method for doing complex plus real. So CC plus 3 is defined in a different location, and the other way around. 3 plus complex. Okay. Now I want you to create a method plus, which will add together 2 endpoints. Okay, so you created 1 endpoint. Now so what we want to do, we want to write this. We want to write A plus B, where both A and B are instances of your endpoint. Yeah, so you have to decide first, what does that mean? Adding 2 endpoints? There could be different ways, but we can just suggest that you just add the X coordinates together and the Y coordinates together. So that could be one notion of adding 2 points. And here's how you could do it. Okay, so you create a Julia file in your VS Code. You must do one thing that is kind of peculiar. You must import the existing plus methods such you can extend them. Okay, so you write this import base, and you have to do it in this weird way. It has to do the 2 dots in front of the plus because it's a special function name. Okay, it's called an infix function, the plus thing. Then you define the new function. So you define a plus. That should be a plus. That's not an X. Sorry. So define the plus function for A, which is an endpoint, and B, which is an endpoint, equal to, here's your function definition. And then try it out. Okay, so let me just quickly fix this typo here. That shouldn't be an X, that should be a plus. Okay, so let's try and do that. Let's see how this could work. You can, if I just put this into the chat, you should really be able to to figure this out quite quickly how this works, because it's almost the same. Okay, recreate and open rooms. Okay, welcome back, everyone. So, how did it go?
I failed.
Yeah, me too.
Okay, good. So let's see how we could do this. So here's our endpoint as before with its two fields. We import the plus function from the base library like this. And there was another typo here, I just realized. No, I'm really sorry. Import base. Okay, maybe that did work. So that's fine. You import the plus function. Then you define a new plus. So that's the main work that we had to do. So function plus, that's the name of the function, A and B. And you create, how do you do that? Or you just sum together the X coordinates of both and the Y coordinates of both, and you stick them into the constructor of endpoint to give you back a new endpoint with those new coordinates. Okay, so that's our definition of what plus of two endpoints means. You could have done it exactly the same way on a one-liner as we said in the explanation. Okay, and then if I just let's see if I can run this whole thing. Just copy it, put it here. So, for example, if I do A 1, 2, B 3, 5.5, and do A plus B, I get 4 and 7.5. Okay, just sum the first two coordinates and the second two coordinates. Okay, so that's a simple demonstration of how you can use existing functions. Of course, the plus function exists in Julia, and specialize it to your own use. And that's a very trivial example, of course, almost stupid, but it illustrates the power that you have as a simple user. You can take other people's functions. They don't have to be part of base Julia. So instead of import base plus, you could have written import something from the distributions package, let's say. Okay, just for example, import PDF from the distributions package. Here you define your own distribution, you know, why not? And then you say, well, how do you do PDF on the distribution? And you say, well, here's how you do it, which means that the entire world can then just use the function PDF to compute the PDF on your data type. Okay, so you can see that that composability makes it very easy for the ecosystem to be very productive, because you don't have to, I don't have to hack the distributions package. You see, I can just import their names and specialize what I want to do with that name on my data type. Okay, good. So that's what we did here. Now let's look at something maybe hopefully a bit more relevant for us. There's an example. Let's call it the worker spell data type. There's a paper by Jean-Marc Robin. What's her name again? At UCL. I don't know. Pia Porndi and Rasmus Lentz. They have this paper on worker and firm heterogeneity, evidence from Danish registered data. I think it's published in Econometrica. And so they have worker spells at different firms in the appendix E1 of the paper. At least when I looked at it, it was in appendix E1. So what do they have? They have 4 million workers and 400,000 firms. Okay, so a bunch of observations. What is a spell? Well, a spell is a certain period of time that a worker spends at a certain firm earning a certain wage. Okay, so, and we just want to keep track of those. So each spell is going to be characterized by a start and an end date, the ID of the worker and the firm, and the vector of wages for each year of that spell. So if the spell was 2 years, then we have two numbers. Let's say the wage is constant for a year, okay, just to make it simple. And then there's going to be an indicator whether the worker changed firm after that spell, because we want to study how workers move across firms and how is that related to wages and worker types. So how do you store that data? And why not a spreadsheet? Okay, so suppose you have a CSV where this data is given to you, and you have each row would be the ID of the worker, the ID of the firm, start date, end date, wage, and so on and so forth. Why not like that? Okay, so that's going to be the overarching question. Suppose what we want to do with this data is to compute the likelihood function, this one. So Li is the likelihood of worker I. We observe this data, wage of worker I in time t, firm of worker I in time t, and x, a bunch of covariates of this worker in time t. And we have that for t to ti, so capital Ti. Capital Ti is the key here because that's different for each worker. Okay, for each worker, we have differently long observation periods. Imagine young workers, they're going to be there for just 1 or 2 periods, old workers for 50 periods, for example. Okay, so the likelihood of worker I will have to, well, that's the likelihood. You multiply all the wage densities, so F is going to be the density of the wage distribution, times S is going to be the probability of staying at a certain firm. M is going to be the probability of moving to a new firm, J prime. And D is the indicator of whether you do move or not. D, you move, 1 minus D, you don't move. Okay, so that's a simple version of the likelihood. But the key thing is that different workers have differently long spells. So the TI is a bit of an issue here. Because if you store that stuff now in a spreadsheet, in order to compute Li, how do you do that? Well, you have your spreadsheet, and then you have to subset that spreadsheet for each worker I, right? Now, the spreadsheet is going to have 4 million times as many periods you have rows, if you do it like this. So I don't know, it's on average 20, 4 million times 20, that's a big number. So that's a pretty long spreadsheet. And now you want to pick out worker number 1. So you have to go through that spreadsheet, look where I is equal to 1, grab that stuff, compute this bit, all right, compute that, and then do that for every worker, 4 million times. Okay, so I'm going to tell you that that's no way to do it. Okay, you will spend the rest of your life subsetting that data frame. Okay, because it's just such a huge operation. You have to create a logical vector that says, where is it? Where is it? I equal to 1. Go there, grab the data, do this stuff. Okay, so you won't finish. Indeed, that's not how they do it. They do it in Fortran with a linked list. And a linked list is something like this. Okay, so we create a mutable struct called spell, where we just collect all the data. So here's what we wanted to know: start date, stop date, duration. You see the data type here is a week, so we can record weeks. Firm ID is just an int. Wage, how much did they earn, and whether did they change firm afterwards or not. And then inside the struct definition, I mentioned that before, we have this function here, which is called the inner constructor. You see it has the same name, spell. You can give it some arguments. So I want to create a spell by saying when does it start and at which firm. Okay, this object is called the inner constructor method. So now I can create one of those by using this function. How does it work? You create a new one inside, it's empty. Then you can put stuff into each slot as you see fit. Okay, here you can do some simple computation to set up this type. I don't know stuff that you need to do in order to compare this. Yes.
Sorry, this function only exists within the struct, or does it exist outside the struct as well?
Yeah, so good question. It's defined inside the struct, but you use it obviously outside. Okay, we'll see an example of how you use it outside. Okay, it's just defined as part of the signature of how to create this thing. You create it inside. You could do the same thing outside, then it's called an outer constructor. Has some different properties. I most of the times use it inside because I think it's just more compact. Okay.
And
now,
can you just recall the first line? Is this equal new parentheses? This is to create a...
Yeah, this creates an empty, so that's a special thing. So that's part of this inner constructor business. Inside a thing, if I call new, it makes a new empty spell. Okay, so there's nothing in it. The fields are all empty, and then I can go over it one by one. I can say, I'll just call it this to say, well, this particular thing that I'm creating, I'll just give it the name this, and I go over each field, start, stop, duration, and I fill in stuff. Okay, That's
And
one way to do it.
Can you do this like outside the struct as a this equal new spell?
Yeah, so the new thing is not going to work if you do the auto constructor. That's the main reason why I like to do it inside, because I think it's kind of clean. So you cannot, new only exists inside this part.
Okay.
Okay, outside if you say new, there's no new. Okay, so outside you have to do it slightly differently, but it's simple enough. So you just, I mean, you can look it up. Okay, let's not waste too much time on this. Okay, so here's that's our definition. That's a spell. Let's create one of those spells. So here I create spell, and I give it a starting date, and I give it a firm ID. Okay, spell, date, firm ID. What does it look like? It's going to create this. It's going to fill in start here. Stop is the same date by default. Okay, I have just to make up something. Duration is 0 weeks. Firm 34. Wage by default 0. Change firm false by default. Okay, fine. So now we have a spell of one worker. Okay, then of course that's not the complete data. So we need a function that kind of fills in the data from our spreadsheet into the spell. All right, so we create a function that we'll call finish. Okay, finish up a spell, let's say. All right, so here what do? We take a spell, S, we take a wage, and we take week. How many weeks did the guy work there? Because I have that in my data. That's what it tells me. Okay, what do? I say finish. You see the exclamation mark is going to modify the input argument. Okay, it's going to modify S. So first of all, I check whether D is actually a positive week, because I'm not going to work with people who work negative weeks, because that's garbage. Then I say, when is the stop date? Well, it's start plus the number of weeks. How long is the duration? Well, it's the number of weeks. What's the wage? It's W. Okay, and then I can do that. I'll finish up the spell that I created before, split. I'll say he earned 100.1 euros, and he worked there for 14 weeks for that wage. Go back to my spell. What does it look like now? Okay, the stop date changed now because it was set to whatever it should be. It was for 14 weeks that I worked there. Wage, did he change firm? No, we don't know. We haven't said that. Okay, so now there's some actual data in my spell. And now I can go on. I can create workers. All right, well, what's a worker? You know what a worker is, but a worker accumulates spells. That's what a worker does. So the worker is a name, is an ID, just a number. He's a number of weeks observed, cap T. Every worker can be observed different number of weeks, of course. So that has to be specific to that particular worker. And I need to know where did he work. So, you know, where's the current firm? That's just an int for the current firm. And this, he carries an entire vector of data type spell with him around. Okay, in his backpack, he has a list of things where he worked before, and I can recall that. So I create a vector of type spell, where spell is the thing we just defined. Again, my inner constructor, how do I build one of those workers? I give him a name. I know how long he lived in this data set. When did he start? What's the current firm? Okay, then I fill again in the fields as I did before, and I give him an array of spell, which is empty at that point. Okay, there's just one spell in it at a certain start date. And then I have to kind of fill in the data as we go along. Let's create a worker. Okay, here's a worker. I'm going to call it Mr. 13. He works at firm 18 for 3 weeks, I guess, and he starts today. What does it look like? Mr. 18 for 18 weeks observed at firm 3, and he has this set of spells. There's just one for now. It's this spell here. Okay. Okay, let's finish up this guy's spell. We have to call the finish function again. Finish on worker 0. Finish up his last spell. I'll just grab the last element of the spell vector. I'm going to say you earn 500 euros for 15 weeks. Okay, we go back. What is this? So now this data is there. It's all collected for this guy. Okay. All right, fine. Well, okay, is this useful? Why is this useful? All right, now we want to use the function. We want to evaluate the likelihood function. We want to sum over each worker for his time that we observe him and see what comes out. So let's try and do this. So I've got 50 workers and 20 firms. I'm going to set some random start dates. So random start dates out of some range. And I set some random number of weeks that I observed those guys, 5 to 10. I'm gonna have a random number, a random ID of firm that you can work at, 1 to F, 1 to 20. And then I'm gonna just crank out a bunch of workers and workers, you see, as a comprehension. See, so works is an array of worker. And long, each of the workers is created with the constructor above. Okay, what does it look like? Here's the log likelihood. So we say the wages are log normally distributed with some parameter. I guess then you would want to estimate those parameters. So that's going to be a function that changes those and looks which one fits the data best. We can then fill in this data. So this bunch of stuff.
I'm sorry, Florian.
Sure.
I'm a little bit lost in the worker struct. When you put there a spell, you call it a vector spell.
Yes.
Is that the full struct spell that you defined before, or because I don't understand why is the vector in there? Why is the what exactly is this vector spell that you're putting in there? Because we defined before the type spell. So
exactly right. Exactly right. Very good question. This is spell, as you well remember. Okay, it's a data type with a bunch of things inside. What I'm doing here, I'm saying in my data set, worker number 1 has many spells. He didn't work just at one firm for his entire life. Maybe he did, but most likely he did not. Okay? Most likely he worked at firm number 3, then at firm number 7, firm number 8. Then he worked at firm number 8, but with a different wage, which for me is a different spell. Okay? So you can see I need many spells. I need to be able to have a set of spells for a single worker. Okay?
Okay, so you are collecting all those spells within a vector that you then pass to the worker.
Exactly right. So the worker is going to have in his backpack a whole list of potential spells, not just one unique spell.
Okay.
And in particular, you don't want to create a data structure for worker spell together, you know, a unique thing that only works for this worker in that spell. That would be totally nonsense. This spell, this set of spells has to be connected to the worker. That's the whole point. Okay, because there are those worker spells, not anybody else's. Okay, so exactly right. The vector word here, this word here says there's going to be a vector, and inside the vector you will have spells, not floats, not ints, not nothing, spells. Okay, good question. That's the key point. Okay, here's just some code where I fill up these things. So you could imagine that there will be the data set in front of this, and I would just grab out stuff of the data set and fill those workers up. Don't worry about it. It just fills in data into the structs. At the end of the day, I'll have workers. All right, these are all of my workers. Worker number 1. What is worker number 1? All right, worker number 1 is called 1. I observed him for 10 weeks, and he currently works at firm 20. Again, here are the guy's spells. It's an entire vector, and there's 6 of those for this person. Okay, so this person has 6 different spells, each of which I can track like that. And I'm not going to open the spell object because you know what it looks like. You can see that here, you know, it says that was the wage, and it says true because after that spell he changed firm. Okay, because he went from firm 1 to firm 18. Okay, so those are all of my workers. And then finally, I can do what I wanted to do all the time. I wanted to sum up with the log likelihood of this thing. And look what this is. That's it. Okay, I say, well, in the beginning, the log likelihood is 0. Then I will loop over my workers. So for IW in workers, for each worker, grab out all the spells, sum to this number, which is the log likelihood, the log PDF of the log normal of that wage. And that's it. Okay.
Why do you need the index in the inner loop there?
Because here I again want to get each spell. Okay, so I go here, I get the first worker.
Yes.
Now for the worker, for each worker, remember what the likelihood looked like. Let's just
yeah, you have different spells, but you are not using the index in there, no?
So I have to do this, right? And so basically the length of this W vector is the length of the vector spells.
Mm-hmm.
So that's basically what I'm doing. And so here, you see, so the length of spells of this guy, of this worker's list of jobs, I go over it like this. I say enumerate that, I get out the index and the spell object in itself, of which I grab the wage.
Yeah, but the index in there, you're not using it within the log PDF,
I'm not using
right?
it. No, you're right. I'm not using it. Exactly
Okay.
right. I could just have said.
No, okay, that's fine. That I was
Yeah.
just.
Yeah,
okay.
exactly. Oh, I see what you mean. Yeah. So. Yeah. So exactly. That's I see what you mean. So I don't use the IDX object here. That's right. Okay. And so in fact, I'm missing half the likelihood because of course there was this other stuff about moving firms, but you can clearly see how I could just add this here. Okay. So there's the part where you move or you don't move and so on and so forth. So that's just an example, but to show you that there's real applicability to those things, because that stuff actually is, you can implement that on a laptop. Okay, that's going to work. And the other stuff with 80 million rows, you need a pretty big data center to do anything with that if you do some sort of subsetting operation. Okay, so just to tell you, you can customize your workload, your algorithm to the exact data you have to work with. And that can be, sometimes our data is very complicated. So that's very complicated data. But so you would just want to build your tasks around the data such that it works best. Okay. So that was the purpose of this example. Any questions about defining custom types? No, very good. Okay, so then I'd say we're ready for a break. So let's do a lunch break and we continue at 2. And let me just quickly, yeah, so I found a couple of updates for, so I found the thing to solve systems of equations and stuff. I'll just send you the notebook that does that, okay? And a couple of links so there's obviously a bunch of material out there, and you can look at that. Also here so it's basically related to this lecture. Where we do, I guess, no, it's the first one where we do this, yes. So if you can look at this lecture at the bottom of this, we use some simple, one-dimensional equation solving stuff. So where should I put this? Should I send an email?
Do we have access to this course? Can we enter there?
Yeah, of course, it's online. You can just go there from. So I think the best point for you to enter this is always to go to my GitHub and to the Julia bootcamp thing, and on the README down here, there's going to be, so here's the homeworks. It's part of this stuff.
I couldn't find these homeworks yesterday. Okay.
Yeah, so I'll clean up this README a little bit, such that you can easier find what you're looking for. Okay, after we're done, so that this kind of.
I just didn't know where to look for them.
Yeah, no, I know it's my fault, but so I'm going to clean this up and make it a kind of more usable resource, so then you can later on go back and figure out what you wanted to know.
Thank you.
Okay, so see you at 2 o'clock. Bye-bye.
Bye.
Bye.
Bye. Thanks.
Bye, guys.
Bye.
Thanks.